Okay, imagine this for a second. You look up at the night sky, but where the moon should be, there's just, well, nothing. An accent. What if the moon was just suddenly swapped out, replaced with a black hole?
Yeah.
It's a pretty wild question, right? It actually came from one of you listening, from Matt.
It's a great what if.
And what's really amazing, I think, is that the answer is, well, it's much less dramatic than you'd probably guess. We're talking about effects measured in, like, milledegrees Fahrenheit.
Tiny.
That's right. It sounds completely catastrophic, doesn't it?
Totally.
But our mission here in this deep dive is to really dig into the physics. What happens if the moon keeps its exact position, but it's just concentrated into a black hole?
Okay.
And the key thing, the fundamental idea is that gravity, from a distance anyway, it really only cares about mass and where that mass is, not what it looks like or what it's made of.
Right. So this scenario, it ends up showing us some really counterintuitive stuff about how space works, about celestial mechanics, maybe challenges some common ideas you might have.
Okay, so let's start with the black hole itself. If you took all the moon's stuff, all its mass, and squished it, how big are we talking? I mean, I'm picturing, I don't know, a golf ball, maybe smaller.
Oh, way, way smaller. That's part of what's so mind-bending.
Huh.
A black hole with the moon's mass, its event horizon, a point of no return.
Yeah.
It would be about the size of a grain of sand.
Grain of sand, seriously?
Yep. Like a single grain of fine sand. Tiny. You can barely see it.
Wow. Okay. Not a golf ball then.
Not even close.
All right.
And the singularity inside. It gets even weirder. For something falling in, it's not really a place, like a point in space. It's more like a point in time, an unavoidable future moment.
A point in time. Okay, my brain hurts already.
Huh. It's definitely strange stuff. Neither here nor there, but then.
So, okay, this tiny invisible sand grain is orbiting Earth where the moon used to be. My gut reaction is still, surely that messes everything up. Earth's orbit goes wonky, the tides go crazy, it just feels wrong.
It does feel wrong, intuitively.
Yeah.
But that's where the physics principle kicks in hard. Since the mass hasn't changed and the position hasn't changed.
The gravity hasn't changed.
Exactly. The gravitational pull on Earth is identical. So Earth's motion stays the same. The tides, they keep doing their thing, pulled by the same mass at the same distance. Think about it like this. If you're floating outside a big sphere, its gravity pulls on you the same down, whether the mass is spread out inside the sphere or if it's all concentrated right at the center.
Okay.
It's the same reason why if the sun suddenly became a black hole of the same mass.
Our orbit wouldn't change, we'd just get very cold and dark.
Precisely. We'd keep orbiting that dark point just like we orbit the sun now. The gravity depends on the mass, not what form that mass takes.
That is actually pretty amazing. Okay, so orbit's fine, tides are fine. What about the obvious thing? No moon means no moonlight. That's got to affect things, right? Like nocturnal animals.
Yeah, you're absolutely right there. No moonlight at all. That would definitely mess with the life cycles of creatures that navigate or hunt or, mate by moonlight.
Yeah.
But, and this is important, compared to all the other massive impacts humans are having on wildlife and ecosystems.
It's probably not the biggest problem they face.
Probably not. It would be, fairly minor in the grand scheme of things.
Yeah.
This black hole moon would actually be incredibly low profile.
How so?
Well, it would be truly black. It would actually absorb more energy from the faint cosmic microwave background radiation, the afterglow of the Big Bang, than it would emit through Hawking radiation. That's the process where black holes are theorized to slowly evaporate over unimaginable timescales.
So unless it ate something, it'd just be invisible, silent.
Pretty much.
Yeah.
Almost impossible to detect directly. Now, if it did start swallowing stuff, like stray asteroids or dust,
then we'd see fireworks.
Oh yeah, you'd get a huge blast of radiation. The accretion disk, the stuff swirling in as it gets eaten. That's one of the most efficient ways in the universe to convert mass straight into energy. Immense energy release.
But there isn't much stuff floating around up there for it to eat, is there?
Fortunately, no. Not really. Our solar system is pretty tidy these days.
Yeah.
So realistically, its main immediate effect would just be messing with the orbits of nearby dust particles. Like one invisible sand grain pushing other tiny grains around.
A cosmic dust buster. That's less terrifying. But you mentioned something earlier that Earth would get colder without the moon, not just the lack of visible light, right?
Right, it's true. Earth would cool down, but we're talking incredibly small amounts.
Okay.
See, people have measured this. Our planet's global temperature actually fluctuates slightly on a cycle that matches the moon phases, about 28 days. And yeah, all else being equal, Earth is technically warmest during the full moon.
Huh. I never knew that. So moonlight does warm us.
A tiny bit. But here's the kicker, the real aha moment.
Yeah.
Most of that tiny temperature variation, it's not actually from the moonlight itself, reflected sunlight.
It's not. Then what is it?
It's mostly because during a full moon, the Earth is actually slightly closer to the sun than during a new moon, just due to the orbital mechanics of the Earth-Moon system orbiting the sun together.
Oh, wow. So that effect, that would still happen even with the black hole moon, since the mass and orbit are the same.
Exactly. That main driver of the tiny lunar temperature cycle would remain unchanged. The black hole doesn't affect that gravitational dance.
Okay, so how much heat does the moon itself actually send our way? Both reflected light and anything else. It sounds like it should be simple, but I guess not.
Yeah, you'd think. But calculating that little bit of energy is deceptively tricky. Science is the worst sometimes. Tell me about it.
For one thing, the phases mean it's not always reflecting the same amount, obviously. And interestingly, a half moon isn't half as bright as a full moon. It's much, much dimmer than that. The way the surface reflects light is complicated.
Right, shadows and angles and stuff. Exactly. But the really significant bit, beyond the visible light, is that the moon gets heated up by the sun, just like Earth does.
Sure, it gets hot in direct sunlight.
And then it radiates that heat back out into space as infrared light, heat radiation.
Okay.
And that infrared radiation coming from the moon, it actually affects Earth's temperature about 10 times more than the visible moonlight does.
10 times? Okay, that sounds more significant, relatively speaking.
Relatively, yes.
Yeah.
But remember, the total effect we started with was tiny. So 10 times more than a very, very small amount is still.
A very small amount.
Precisely. We're still talking about maybe 10 times less warming than the effect of Earth just being slightly closer to the sun during the full moon.
Okay, so can we put a number on it? How much warming do we actually get from that infrared moonlight?
We can. It works out to about 1.2 milladegrees Fahrenheit.
1.2 thousandths of a degree Fahrenheit.
That's it. Or, 1.2 milladegrees Rankine, 0.35 milli something called a radar, 0.53 milligrays, 2/3 of a millidegree Celsius. It's minuscule, however you slice it.
So losing that heat source, Earth cools by about 1,000th of a degree. What does that mean, practically? Anything.
Practically. Almost nothing. I mean, yes, the planet would cool down ever so slightly, but given the rate humans are adding CO2 to the atmosphere, changing the planet's energy balance in a much bigger way,
And make up that tiny difference pretty fast.
we'd probably make up that 1.2 millidegree difference in like a couple weeks of business as usual.
Wow. Okay, so wrapping this part up. Swapping the moon for a same mass black hole. It sounds apocalyptic, but the actual impact is, well,
All in all, yeah, it might not actually be that big a deal for life down here. Pretty underwhelming in a way.
it really makes you think, doesn't it? The famous quote from 1969, "One small step for man." Imagine if it had been, that's one small step onto. Well, nothing's here, but the gravity feels about right.
Oh, doesn't quite have the same ring to it.
Not really. But okay, let's pivot for a second, because there's a really critical distinction here that often trips people up with black hole hypotheticals. We've been super careful to say a black hole with the same mass as the moon. What if? What if we ask the question differently? What if the moon were replaced by a black hole the same size as the moon?
Now that is a completely different kettle of fish.
Yeah.
And much, much scarier.
Why is that?
Because a black hole that was physically the size of the moon, meaning its event horizon, stretched across that 3,500 kilometer diameter.
Yeah.
That wouldn't be a sand grain anymore. That would be an object of truly unimaginable mass. To have an event horizon that big, a black hole would need to have something like 600 times the mass of our entire sun.
600 times the sun's mass sitting where the moon is now.
Exactly. And the gravitational pull of that, it would be catastrophic. Forget stable orbits. The Earth, the inner planets. We would absolutely, definitely fall into it.
Yeah.
Very quickly.
So that would be it. Game over.
That would be the total final lunar eclipse for us, yes. The end of everything. So same mass versus same size.
Yeah.
Not a minor detail.
Yep. No kidding. It's absolutely crucial. It's just fascinating how the scenario we started with, moon turns into a black hole, sounds like the end of the world, but under these specific conditions, keeping the mass the same.
It turns out to be surprisingly benign, almost boring from an effects standpoint.
It really drives home how counterintuitive physics can be, doesn't it?
Yeah.
And how much precision matters in these thought experiments. Every single detail changes the outcome completely.
It absolutely does. And it kind of teaches you a lesson, I think. Sometimes the really dramatic sounding changes, if you define them carefully by the physics, they have less impact than you'd think.
Yeah.
While other things, seemingly small details like infrared heat or tiny shifts in orbit, those can actually be the more influential factors on a planetary scale.
It makes you realize how much is going on beneath the surface governed by these subtle forces we don't usually notice.
Definitely. A lot of the universe's workings are, well, hidden in plain sight, driven by things that aren't immediately obvious.
It really does make you think. So maybe a final thought for you listening. Think about how our gut feelings about big, dramatic events can be so far off from the scientific reality. How much of the universe's machinery operates on these subtle, almost invisible rules? And maybe, what other huge, scary-sounding what-ifs might actually turn out to be surprisingly mundane if we really did a deep dive into the specifics?